Hello, welcome to the Area Solutions channel. In this video, we'll be looking at solutions to problems in kinetics, and then we're going to walk through an example that involves a 12,000 kg vehicle which enters a 10-degree steep ramp at a speed of 25 meters per second and travels for 5 seconds before its speed was reduced to 12 meters per second. Then we're to assume constant deceleration, and we are to determine some variables: braking force, the time required for the vehicle to stop, the deceleration of the car, and the total distance traveled by the car. So let's start by looking at some of the things that we have. We said the vehicle entered a steep, and we're given the mass of the vehicle to be 12,000 kg. That is to say, the weight of the vehicle is 12,000 kg times 9.81 in all the newtons. And then this vehicle enters a steep of 10 degrees. So that is to say, the part that the vehicle is moving on is inclined at an angle of 10 degrees. And it enters that ramp at a particular speed of 25 meters per second. Then other things that were given to us, we were told that when the time is 5 seconds, as it's moving along that path, velocity was reduced to 12 meters per second. Then we have to assume constant deceleration and calculate for certain variables the magnitude of braking force, the additional time required for the truck to stop, the deceleration of the car, and finally the distance traveled by the vehicle. So two variables quickly will be determined in this video based on this particular question that has been given to us. Let's start with what has been given to us. We've been given initial velocity 25 meters per second. So we've been given a time of 5 seconds. And we have been given a velocity of final velocity of 12 meters per second. But to look for the magnitude of the braking force based on these variables. And looking at the vehicle that we have, what are the forces acting on the vehicle? We have the weight of the vehicle. If we assume a coordinates of which one of it has the horizontal is parallel to the direction of the vehicle and the other is perpendicular to it, we have that the weight of the vehicle is at an angle of 10 degrees to the coordinate that is perpendicular to the direction of the car. That can be gotten geometrically. And if we choose to resolve this weight of the vehicle into two different components, so we have one in the direction perpendicular to the direction of the vehicle, and we have another one normal to the direction of the vehicle. And this is just and this is gotten by just multiplying by the sine and cosine of the angle for the respective directions. And finally, we have the braking force. So that is to say, we have two key force components that are acting against the direction of the vehicle, and we have one that is acting perpendicular to the direction of the vehicle, and that can easily be neutralized by the reactions from the road. And then we're to call in our various kinematic relation. The first one is the Newton's second law that relates summation of forces to mass, to the product of mass and acceleration. Of course, this can be suitable because we can easily get the value of acceleration from the different values of velocities and the time that is given. But that would mean we may need to work out the acceleration first, introduce the value of the mass, and then estimate the value of the force. Then also we have the energy equation, the particular equation that relates the work done to kinetic energy for a moving particle. But this may not be suitable because if we want to calculate work done, we don't have distance that the vehicle has covered. However, this can be calculated based on the variables that has been given to us. And there's a third relation that relates impulse and momentum. The impulse and momentum equation can be used directly to estimate the braking force, as the impulsive force is a summation of all forces acting on the vehicle. So we're going to work with this equation because this equation does not require us to apply any of the kinematic relations. So using this equation, we are going to first look for the value of impulsive force. How can we get impulsive force? We know that impulse is the product of force and time. Since impulse is force times time, what are the forces acting on the vehicle? And we can quickly see that the total impulse, or the summation of impulse acting on the car, is the sum of the impulse of braking force, as well as the impulse resulting from the component of weight of the car acting in the direction of motion of the car. Well, these two force components are taking the negative sign because they are acting in a direction that is opposite to the direction of the car. And we have our equation to be initial momentum plus total impulsive force is equal to the final momentum of the vehicle. Then these are the variables we have: the initial velocity, the time, the final velocity, and the mass of the vehicle. So we can quickly put all these variables back into the equation. We have the part for initial momentum, which is mass times initial velocity. We have the part for the total impulsive force, which we estimated earlier. And we have the part for the final momentum, which is the mass times the final velocity, as at when the time was 5 seconds. And note that in the place of time, we've put 5 seconds as if in the impulse component. So having done all this, we're going to walk through this equation to find our braking force. If you simplify the equation, you get that our braking force will be equal to 10,750 newtons. And that's our value for braking force. So we go on to solve other parts of the problem. The second question asks us to find the additional time required for the truck to stop. Let's quickly note that as at that point in time, after the car moved 5 seconds, we're asked to look for the additional time from that 5 seconds, from when the velocity was 12 meters per second to when the vehicle will come to stop. So we have that final velocity, because the vehicle will come to stop at that time, is equal to 0 meters per second. And we have the velocity at the instance we are looking at to be 12 meters per second. Let's note this: it's vital we understand why we're using 12 meters per second. This is because we are looking for additional time required for the vehicle to come to stop. That means as at the time the vehicle had traveled 5 seconds, when it was 12 meters, when the velocity was already 12 meters per second, to when the vehicle will come to stop. That's why we're picking 12 meters per second as against the initial velocity of the vehicle when the car just entered the steep ramp. So if we're working with that, we had our mass. Which equation is most relevant? If you look at your three kinematic relations, you'll notice that it's just the impulsive equation that relates both momentum and impulse that can suitably be used to estimate time, because this is the only component of all kinetic relations that contains time. So if we're going to work with this, we've estimated our impulsive force earlier to be the product of all forces acting on the system multiplied by time. For this case, we had just the braking force, and we had the component of mass that's acting in the opposite direction of the car. So if we're working with this, and we take all this that we've known into the basic equations, we have mass times initial velocity plus the impulsive force component is equal to the final momentum of the vehicle. So if we're working with this, let's not forget that we've estimated our braking force to be 10,750 newtons earlier. So by the time we put all that we have into the equation, we're going to have one straight equation. And with this equation, we can simplify. Let's note that in this case, we are looking for time. So we've input the value of the braking force into the equation, and we're going to simplify further to calculate the value of time. And for here, it's going to be 4.62 seconds. Now, let me present to us something else. What if we are to look for total time traveled when the brake was applied? Total time traveled. In this case, not that brake was applied, but it entered into a steep road that was going to bring the vehicle to stop. Now, the total time traveled by the vehicle before it came to stop when it entered that road, considering that the vehicle had constant acceleration, we have that our basic equations this time around remains the same as the impulsive equations, but this time around we're going to use the initial velocity, because we're looking for total time the vehicle traveled. That's, you are saying, when the vehicle entered the steepy part of the road to when it came to stop. And as at the time it was entering the steepy part of the road, the velocity was 25 meters per second. So we're going to work with that. And we know that the final velocity is 0 meters per second. And we've calculated our braking force earlier to be 10,750 newtons. If we put all that into our basic equations for momentum and impulse, when we simplify, we get our time calculated to be 9.62 seconds. Going forward, we can just see that initial time traveled before the vehicle got to 12 meters per second as given in the question is 5 seconds. And we also had the time spent after then to when the vehicle came to rest. We also calculated that earlier to be 4.62 seconds. Then we see that the total time traveled will be the initial time it took the car to get to 12 meters per second plus the time it took the car to come to rest, which is 4.6. If you add this up, you get 9.62 seconds, which is equal to the time we calculated using our basic kinematic relations. So this is just to cross-check what we've calculated earlier. So we're going to go forward to calculate the deceleration of the car. Which equation is most suitable? Equation we have to answer considering all the equations that we have. We know that the only equation among the kinematic relations that has acceleration components is the first one. Summation of forces equal to mass times acceleration. So this is the one we're going to use to estimate the acceleration of the vehicle. So if we're using this to estimate the acceleration of the vehicle, we have to consider what are the forces acting on the system. For this case, we see that the summation of forces acting on the system, especially in the direction of movement of the vehicle, we have just two key components. The one as a result of the weight of the vehicle, and the other one which is the braking force. So if we bring all this into our equation, we have our summation of forces to be negative values of the braking force plus negative values of the component of the weight acting on the system. So if we equate this equation to be equal to mass times acceleration, we can quickly call the values of the braking force and the value of our mass and put them into the equation and work it out simply to estimate our acceleration. And if we do that, we're going to get acceleration to be minus 2.6 meters per second square. So we want to cross-check if our answer is correct. There are basic kinematic relations for calculating acceleration. We have that v equal to u plus at. Acceleration is equal to v minus u over t. And then we can have different variables that has been given to us. Initial velocity, final velocity, and the total time traveled. Note that we're starting with 25 meters per second as our initial velocity. So the total time for the vehicle to come to rest, that is for v2 to be equal to 0 meter per second, is 9.62 meter per second. Is 9.62 seconds. So if we put this into the equation for acceleration, we get our acceleration as well to be minus 2.6 meter per second. However, we can choose to use other aspects of the problem. We can use our initial velocity to be 25 meter per second. We get our final velocity this time around, which is 12 meters per second, but the time it took for the vehicle to get to 12 meters per second is 5 seconds. So if we also use these variables to estimate our acceleration, we as well get minus 2.6 meters per second. Well, some other person can say, no, I'm not interested in these variables. Let's use another instance where we're considering when the car started moving from 12 meters per second to when it came to rest. We calculated that time to be 4.62 seconds. And if we put all this into the equation, we can quickly calculate our acceleration as well to be minus 2.6 meters per second square. So regardless of the scenario, you see that there are a lot of variants or a lot of possibilities, but you always arrive at the correct answer. But just be mindful of how you select the variable you're using to do your estimation. So we're going to move on from here to calculate the total distance traveled by the car. Well, we're going to call our three kinematic relations again. We see that the only equation that is suitable for calculating distance is the one that relates energies, kinetic energy and work done. And this is so because we know that work done is the product of force times distance. So we're going to work with the last equation to calculate total distance traveled. So if we call our equation, the first thing of concern is what is the work done? Work done is force times distance. So the total work done is the sum of all the forces acting on the vehicle multiplied by the distance traveled by the vehicle. But of course, for this time around, we are looking for distance. So we have all our variables given to us. We have our work done is equal to force times distance. Then if we consider the two forces, which is the component of the weight and the braking force, all that are acting against the direction of the car, the moving vehicle, if we put that into the equation, we get our work done to be equal to force, braking force times its distance, plus the component of the weight acting on the car against the direction of the car times the distance. Mind you, note the reason for the negative sign for force components, the braking force and that of the weight. The negative sign is just implication, it's just an indication that they are acting in the opposite direction of the moving vehicle. So if we walk through our equation, if we input everything back into the equation, we have the component of initial kinetic energy half mu square, where u is the initial velocity as the car enters the steepy points, and we have our value of mass to be 12,000 kg. We have our total work done to be the summation of the force and the distance, all the forces acting on the vehicle multiplied by the distance, capital letter ox, and the final component, which is the final kinetic energy, to be equal to half times mass times final velocity square. Let's not forget that our final velocity is 0 as at the time the vehicle had come to rest. So if we walk through this equation, we can easily and quickly calculate our distance to be 120.2 meters. Well, let's try to see how we can use kinematic relations to estimate the distance. We have that s is equal to ut plus half at square. That is, distance is equal to ut plus half at square. So what are the things we have? We have initial velocity u. We have our total time before the vehicle came to rest to be 9.62 seconds. We have our final velocity to be 0, and we have our component of acceleration to be minus 2.6 meters per second squared. If we put all that into the equation, we have, and we simplify, we're going to get x to be 120.2 meters. Well, if that's not enough, we can use another kinematic relation, v squared equal to u squared plus 2as, and we can calculate our x to be the difference in the velocity squares divided by 2a. If we input all our variables that we have into the equation as well, we also get 120.2 meters. So this is all about all that we've been required to estimate. Just to summarize, we had a problem given to us. A vehicle enters a steep part of a road, and the initial velocity was 25 meters per second. The steep part of the road is inclined at 10 degrees. And then, of course, there was time given to us 5 seconds, and the velocity at that time 12 meters per second, as well as the mass of the vehicle. And we were asked to calculate braking force, which we did to be 10,750 newtons. We estimated the time for the vehicle to come to stop to be 9.62 seconds. We estimated the additional time for the vehicle to stop from that position of velocity to be 4.62 seconds. Then we determined the deceleration, which was minus 2.6 meters per second square, and finally the distance traveled by the vehicle to be 120.2 meters. I think this will be all for now. I want to thank you so much for your time, and please do well to subscribe to my channel, as I hope to see you in subsequent video.